Okay. All right, we are live. Good morning, good afternoon, and good evening, everyone watching at home. My name's Sophia. I'm the multimedia technician. I'm behind the camera right here, if you can see my hand. We are live today from RV Falkor 2, vessel run by Schmidt Ocean Institute, and we are on our Dynamics of Sinking Microplastics expedition. And here in front of you, you can see our panel of microplastics experts. I'm going to get them to introduce themselves in just a minute. As always, because this is a live stream, you can feel free to put your questions in the chat. And at the end of our little lab tour, we're going to be answering those. So yeah, carry it away. Laura, if you want to introduce yourself first.
Hi everyone, I'm Laura Simon, a postdoctoral researcher at Aalborg University, Denmark. I'm also a National Geographic explorer, and through the collaboration between the Schmidt Ocean Institute and National Geographic, we came on board of the Falkor 2 to explore the sinking dynamics of microplastics. And we can...
Yeah, hello everyone. I'm Jeanette Lykkemark. I'm a PhD student at Aalborg University, and I'm helping Laura to get this sample here on Falkor 2.
Hello, my name is Elvisa Vianello. I am associate professor at Aalborg University, and like Jeanette, I'm here to help Laura to collect good and many samples on board of Falkor 2.
Yeah, hello everyone. My name is Asbjørn Nielsen, and like Elvisa, I am also associate professor at Aalborg University, helping you out on the sample expedition.
And before we explore all the really cool equipment we have on board, I would just wanted to ask, could somebody explain to me just the premise of what microplastics are?
So microplastics are pollutants that are the small plastic pieces of plastic that are accumulating in our environment, not only in our ocean but also on land. And in general, they are defined as plastic particles smaller than 5 millimeters.
Cool. Very cool. Shall we go see the CTD in the hangar? Amazing.
Maybe one thing that we forgot to tell everyone is where we are. We are offshore of Panama, and we are reaching the coast right now.
Amazing. After you all.
Oops.
Oh.
I will say maybe this is the CTD hangar, and we have spent quite some time over the last days over here, from day to night, all time, filtering water. That is the way that we are capturing the microplastics. And mostly we have been using two systems, that is the rosettes that you can see. So all of these rosettes, this rosette is composed of 24 bottles that they collect 12 liters of water each of them.
And then we have our nicely designed equipment here from Aalborg University down here, which you see have like these 12 arms. So from each tube we can place this into the arm and one on the other side. So we have all 24. And then from here we can attach a metal tube, and on that way we can filtrate all 24 bottles and the 12 liter. And Laura has a tube, so
yeah,
you can see.
So I will say first we can characterize the water column and see the different parameters, that it might be the temperature, the salinity, and also the density along the water column. So like this, we are choosing different depths. Once we decide the depth that we are targeting, we are closing all these bottles at the same depth, And we filter all the water using this system into a custom built device instrument designed at Falkor University that is called UFO, but the guys will explain you afterwards in detail about this instrument. And one important thing that maybe a lot of the audience is wondering is, okay, they are looking for microplastic, but they are using PVC bottles. And also another thing that we can see in this instrument are these springs or lines that are made of nylon. But we are aware of this potential contamination, and what we will do in our results to subtract these special polymers or specific polymers, so we can track what is actually coming from the ocean regarding what is coming from the instrument.
Yeah, the reason for closing all the bottles at one depth is to make sure that we have enough volume, because if you only take like 12 liters out of the whole ocean is not so much, where if we take and close all 24, we get a much higher resolution. Yeah.
What are some of the depths that you are closing the bottles at?
The deepest one we have gone during the cruise is 3,200 meter depth. So we are pretty excited about that sample because we
3,000 is.
So we will have a complete overview of the microplastic abundance along the water column.
Yeah, and then when this guy and we have decided the depths, we then also send the McLean pump down, which is the second thing we use out here.
Here, I'll come around this way.
So, as we have mentioned, with the rosette we are filtering almost 300 liters per depth, but when we go to the McLean at 5,000 meter depth, and what is the difference is with this one we are almost filtering 1,000 liters of water. So the idea behind this comparison or using these two instruments is to have an overview what are the results that the different instruments can provide, so we can have a comparison, because in the future it's very easy to have access to a rosette in a research vessel, but not so much to a McLean pump. So we want to see what is the representativity of this instrument to study the presence of microplastic along the water column. And we can also show...
Yeah, so this is the filter that we put inside. This has a size of 10 microns, so the things that can get through the filter is quite small. And I don't know if you can see it here, but this filter went down to 15 meters, and there's like a cake on top of it. I hope you can see it out there. Yeah.
And what you might be wondering is that you don't see microplastics, but we are really looking for the very small microplastics that are not visible to our eyes. So this sample will go through a long sample preparation once we are back in the lab to extract this particle from the organic and inorganic matter that is present in the ocean.
And something other worth mention is maybe that if you look at our clothes, we are wearing cotton shirts to make sure that we don't also contaminate our samples from our clothes. And furthermore, we also, every time we do a sample, we also have this air blank that we open. Yeah.
At every station, every time our filters get exposed to the air, because there are microplastics in the air that are falling down, and we want to prevent or to track back the potential contamination from plastic around us versus what is really in the ocean. So we are using these blanks to capture these airborne microplastics. And another thing that we do, everything before getting on board was muffled up to 500 degrees. So what we make sure is that the organic or potential plastic particles that were present in our glassware was completely gone.
Yeah. How does muffling work? Could you explain a little bit?
Yeah, sorry. It's like an oven that it can go up to 500 degrees. So we wrap all our glassware with aluminum foil, and we place it there for over 5 hours. And it follow a temperature ramp until it reaches 500 degrees, and then it stays there for more than 4 hours and then we let it cool down and bring it with us. And we do this for the sample preparation, but also every time is a regular basis in our lab to prepare all the glassware that we use.
Yeah, and we wrap it in the alufoil before, so that we don't contaminate it when we take it out.
Mhm.
Yeah.
And maybe we can show the setup. So the idea is when we are using the rosette, we connect these hoods that are made of stainless steel, so we make sure to minimize the presence of plastic in our system. And if we go back to the setup, well, every time when we bring back the rosette, we connect to the system for the filtration.
Very cool.
Yes.
Thanks for showing that.
And from there, all the water gets to the pump that will make it flow through our UFO systems. And here you can see how our instrument is looking, but the guys will take over for explaining you.
Sure. Before they explain the pump, I'd love for you to explain a little bit about how the McLean pump works and how it's set up with the CTD as well. I want to give the audience a sense for how that looks like when it's actually being used.
So the idea is it works as a pump. So here we have the head of the McLean that is, if we open it, you can see where we place the filter. Here we place the filter that Janetta showed before. So once we set up the filter, we send it into the water. And for example, in our deepest point, when we went down to 3,000 meters, what we did it was to attach the McLean on the same line than the CTD with 20-meter difference. And the idea is that going very deep in the ocean, it takes a lot of time. The deployment down to 3,000 meters, it can take up to 5 hours. So by this, we reduce the time that the instruments are deployed because the time at sea is expensive and we want to make the most out of it.
Yeah.
Yeah.
And maybe you can show the flow meter. So
Yeah, it's on the other side. So it's down here. So every time before sending the McLean down, we read how much the flow meter is at. And then when it comes up, we need first to empty the leftover waters in here. And when that is gone, we read it again and we note down exactly how many liters of water that we have filtrated, so we can, when we have finished the filters, we can put it back and say how much microplastic there is in 1 cubic meter. Yeah.
Amazing. We have a question from the audience saying, what do you use as your baseline tests?
I guess as baseline test, it refers to a control sample. And in general, we have the control. We have two different type of control. One is the sampling blank. That what it does is to track the potential deposition while we are sampling. But then once we go into the lab, we have another control that it will be pre-filtered water down to 0.7 micrometers. So what we do is to treat this water similar to the sample preparation that we do. So we can see we introduce some potential microplastic along the sample preparation, and then we correct all our results based on this control.
Very cool. Thank you so much for explaining that. If you're ready, we can talk about the UFO system. Take it away.
Yeah.
Here, I'll position myself in a more ideal spot. There we go.
So the UFO system is a filtration device. And what we have here is we have basically two setups that we run in series with different size filters. And what, if you look down here, for the water from the CTD, it goes through the pump, and then it enters the first device. And I guess you can all see why we have named it a UFO, because of this nice shape. It looks like it had just landed. But what it consists of is that it has a volume here, and In the middle, it has a layer where we can position the filter. And then we
One
will,
minute, I'm just going to go on this side. Sorry about that. Go ahead.
then we will use different filter sizes. So first we have a pre-filtration of 300 microns. And then we have smaller filters here where we're using 10 micron filters. And those are, you can see the flow line is here split in two. So we do a parallel filtration where we capture particles down to 10 micron. And then for this cruise, we're trying to push limits of how small particles that we can analyze, because currently we are good to go down to approximately 10 microns, but we want to try to go down to 1 micron. So therefore, we have placed in series another setup where we do first a 5 micron filtration, and then we have again in parallel 2 1 micron filters. And similar to the McLean pump, we keep track of how much water we are filtering, so it also has a gauge here so that we can read the volume of water that we have filtered. For this setup, when it is connected to the CTD, we are limited to the volume that the CTD can contain, that we are able to retrieve from the depth. But we also have a large volume filtration system where we are using the ship intake water, which we can take a look at.
Yeah, if you want, we can show you another location, another laboratory where we have some other UFOs that are filtering water from another part of the ship, the so-called ship intake. And in the case of Falkor 2, the water is collected through a plastic-free pump or system, piping system, and we will show you the seawater lab very soon. So
Okay. Hi, everyone. Sorry for the little pause there. We had some audio issues. Thank you for bearing with us. Avisa will now show us the seawater lab. And yeah, take it away.
Okay, welcome back, and sorry for the inconvenience, but as you know, when you go live, these things can happen. So welcome to the Science Seawater Lab of Falkor 2, and follow me in. So inside this room, there are a lot of things going on, and a lot of sensors that Falkor has on board on a regular basis, and you can measure the pH and many other parameters that are really important when you are doing marine science. But since we, came on board this incredible research vessel, what we did was to install our UFO system, or in this case, our two UFO systems, to do something similar to what Esbjørn previously explained you. But in this case, instead of filtering water that has been collected with the rosette bottles in the CTD hangar, we use the microplastic intake or ship intake that the guys set up in this ship, because it's like a plastic-free pipe that is like collecting water from outside the vessel at a depth of around 4 meters, and in this way we can pump water inside the lab, and from this tap that you can see here we connected our devices. There are two devices because what we are trying to do is to replicate the same setup we have just outside. So again, we have a first UFO system that is filtering water at 300 micrometer and then at 10 micrometer, and after this first stage of filtration we have another pipe that is connected to the second system, and in this first UFO we have a 5 micrometer filter, and then the flow is split in two down to 1 micrometer, so we can catch even the smallest microplastic that are out there. As you can see, if you come closer, you can clearly see the system is actually running right now, and this very simple flow meter that maybe some of you already saw at home to measure the consumption of water, instead in here is telling us how many liters of water we are filtering. And after the flow meter, we have the outlets to our custom-made device. We can filter quite large volumes of water, and since we are connected to what is called the ship intake, we can do it while we are standing still at station and doing the other operation in the CTD hangar, or we can do it while we are sailing, like we are doing right now. So why we do that? Because as my colleague already explained, the ship time is very precious, and we want to get as many samples as we can. So instead of just taking samples while we are in one station or in another, we also collect samples while we move from one station to another. This not only increases the number of samples we collect, but also it can tell us how the concentration of microplastic varies in this stretch that we are covering right now. And
yeah, and as Laura explained earlier, we are off the coast of Panama. So we are in one of the busiest ship lanes in the world, probably, and one of our key aims was to look at the gradient in concentration. So we expect that there will be a higher concentration close to the Panama Canal, and as we migrate further out to sea, we hope to see lower concentrations of plastics in these transect samples.
Very cool. Do you expect the different sizes to be present in different ways throughout the water column?
That's a good question, a $1 million question. I mean, the type of research we do, it's quite forefront, it's quite state of the art, so there are not so many data available, but we think that we might also see, while we use this system with the ship intake, a slight difference from the coast up to the out to the offshore waters of Panama. As Esbjørn mentioned, it's a really interesting study area because of the ship traffic, and you might know that, I mean, ships, they contain a lot of plastics because, of course, I mean, there are many things that are made of plastic on board of the ship. But there is another detail that maybe is important to mention, that all the ships are painted, and many paints, they contain polymers as well. And on top of that, they contain other chemicals that are called biocides, that are used to prevent the organism to attach to these painted surfaces. And biocides are, meant to harm or to kill living organisms. So all these paint flakes that can shed from the ship, they are for sure harmful to marine life. And we want to know or to understand if a high trafficked area could also be highly impacted by microplastic or micro paint particles. So yeah, that's why we are using this underway system to collect water down to 1 micron. And it's going to be quite some work back in the lab, but we are really, really curious to see how much or how many microplastic we will find in a few months.
Very cool. I think we could all do like final questions here. It's not too loud, so I don't want to keep y'all hanging. I have some comments about some folks. Yep. I have some comments about some very concerned folks at home that are wondering maybe like what can we do to reduce our plastic or microplastic outtake and that's like affecting our ocean so much.
Laura, you want to give some advice on it?
Yeah, I would say it's a difficult question because it starts by a change in the way that we consume plastic in our daily basis, but it also goes to a larger scale that it has to involve many more parties than not only the individual change. So the first thing, and it might seem easy, is just to reduce the single-use plastic that we use every day. But we have to consider that as humans, and we are using plastic, and they are an amazing materials that we can use for many different applications. We are impacting just by the fact that we are in our daily life using synthetic clothes, that they are also shredding microplastics. So the limitations goes from reducing the single-use plastic to reduce the beach littering when we are. So it's a change in the way that we perceive, we treat our environment, and also it has to go to a major scale change.
Thank you for that. That was a very good answer. I also, at the beginning, when you talked about the jar of air you had in the hangar, could you tell us a little bit, I know your focus is microplastics in the water, but could you tell us a little bit more about the microplastics that we can find in the air as well? That was really surprising.
Yeah, actually, because in our lab we are targeting different environmental compartments, and the air is one of them. And what we see, especially in indoor environments, is that the concentration of microplastic is relatively significantly higher than what we found in the ocean, and particularly the smaller microplastics. And while we have our body, Alvise can explain a bit more because he did one article specifically targeting indoor environments, so he can elaborate on the results. But
yeah, I mean, I think you already covered most of it, but yeah, it's quite striking. But yeah, there are microplastic in the air. They are suspended. They travel long distances because they are light and they are small, so they can stay in our indoor environment, meaning in our apartment, for example, we find quite a high concentration of microplastics. And this is because there are many plastic items. Our furniture can contain synthetic textiles, and so we find a lot of them. And the smaller they get, the higher is the chance that we don't only inhale this plastic, but it can also be deposited in the deeper part of our airways, and when it gets there, it could get stuck and cause some irritation of our airways and some negative effects that is still a bit unknown, but it's quite alarming. So yes, unfortunately, microplastic is not only a pollutant that is like affecting our ocean, but it's I would say everywhere. I mean, in our soil, in our freshwater environment, so the rivers, the lakes, even in our apartments, and potentially also in our lungs. So it is really important that we do some science and some research to better understand how harmful these pollutants are, because we just started to scratch the surface of it. We started probably less than two, and how we can impact.
We've also got some questions. I was also personally wondering this, what your analysis.
Well, we do this sample preparation because you saw the filter and there was this cake, and from this cake we need to somehow isolate the microplastic. So we do a lot of different steps, including different enzymes treatments, so get rid of cellulose or protease or all these stuff that can be in there, and then also we want to get rid of the inorganic parts, where we do density separation. And density separation is where we have the lighter microplastic laying on the top, and then we get the heavy inorganic parts
Yeah.
falling to the
More dense or heavier particles are some salt solution. You can also do it at your home if you want by using kitchen salt, because I mean, if you put a lot of salt in the water, then you increase the density of the water, and basically most of the plastic will start to float, and if instead you have some grains of sand, they will sink to the bottom of, for example, a glass. So we do something similar. We just don't use kitchen salt, but some other specific reagents for that you have in the lab. But after all this very time-consuming process, to really understand how much plastic and which type of plastics, what we have in the lab are quite fancy and expensive instruments. I would say that our most used instrument is an infrared microscope. Actually, we have two of them because we have a lot of sample to analyze. What is an infrared microscope? Is a microscope, so you can see very teeny tiny objects, but on top of the microscope there is also like some infrared light that is like impacting the sample, and then different materials, they absorb infrared light in a different way, and that's how we can characterize materials, including polymers, which are the components of plastic. But to push the research to new limits and analyze the very, very small plastic particles, we use another instrument which is called Raman microscope, which is a very complicated instrument, but basically it just has like a different laser that they can go and hit these microplastics, and in a similar way to the infrared microscope, they can provide you a fingerprint that is specific for each type of plastic. This way we can say how much plastic is there and which type of plastic, and also how big or small they.
There we go. Okay, go ahead.
Yeah, we are missing one analytical method, which is the one I'm using mostly. It's pyrolysis gas chromatograph mass spectrometry, which is basically where we heat our sample up without oxygen, and then they break down, and this is then being separated in the chromatograph, and then we analyze the different mass, and that way we can also fingerprint it back to what we had in the beginning, so which type of plastic we had. And the advantage of this machine is that it gives us the mass, where the other we have to estimate the mass. And potentially this machine would also be able to go down to the very small, as long as we have enough so we are above the detection limit. Yeah.
And you can say for the two microscopic methods, so the drawback of the infrared microscopy is that the infrared light, it has a very long wavelength, and we are not able to see items that are smaller than the wavelength. So the benefit of the Raman is that we use a laser which has a shorter wavelength, which allows us basically to see smaller particles.
You
And-
want to?
And maybe one thing to say about the instrument that Jeanette is using in the lab is that it's capable also to analyze another type of so-called microplastic that are the little pieces of car tire rubber that they are released from the tires while you are driving your car.
Oh,
And these
cool.
pieces are black, they contain a lot of carbon black. So the other two instruments, they cannot detect them, but the pyrologist GCMS can, and it's important to do that,
Yeah,
right?
For example, in Denmark, where we are all located, it is estimated that more than 55% of the microplastic comes from car tires. So that's why it is also very important to understand the impact. And also because tires also have a lot of different materials and chemicals, and this can also be leaching into the environment and potentially be harmful to the life and to the environment. Yeah.
Yeah. I would say that you touched like a very good point that maybe we should share with the audience, is that plastic is not only plastic, okay? When some polymers are manufactured, there are also a lot of other chemicals that are used to give specific, properties or features to the plastic. Unfortunately, when plastic is dumped into the environment and it's subjected to, photochemical reactions. So when the sun is hitting on the plastic, is oxidizing, is degrading this material. All these chemicals that are inside the plastic can be leached out. So we are not only talking about a pollutant as a particle itself that can be ingested by marine life or even humans, but also it can contain a lot of these chemicals that when they get leached out, they can be even more dangerous than the particles themselves. So it's important to remember that plastic, it's not only teeny tiny particles or microplastics, but they contain also chemicals that can be even more harmful to living organisms.
Yeah, and once they are degraded, also rather than leaching, they can absorb another pollutants. So they are also a vector to transport these other pollutants as just the particle itself.
Wow. Yeah, we've got some comments saying they didn't even know that was a problem. You all explained microplastics so well. This is very cool. There's also some questions about remediation. There have been some studies about bacteria and funguses potentially eating plastic particles. And so could you tell us a little bit more about those types of remediation methods?
I mean, there are some studies that are showing that some microorganisms could effectively degrade plastic, but I mean, so they are promising, but I think there is much more research that needs to be done before telling the people, okay, we found a solution and we can bioremediate plastic pollution using microorganisms. So it's true, I agree with the comments from the audience. There are some studies that show some effectiveness or some efficiency in degrading plastic with microorganisms, but I think we are still in an early stage of this type of remediation.
And also, I would say that a lot of these studies are conducted in laboratory conditions, and we cannot apply this bioremediation process into the ocean. For example, where we are targeting the 3,000 meter depth, we cannot directly apply this bioremediation process.
Yeah. I don't know, maybe Espen, I mean, you are an expert also in treatment of urban waters.
Yeah, we have done some studies on wastewater treatment, and one thing that we have found is that the conventional wastewater treatment systems are quite effective at retaining plastics. So maybe more than 99% of the plastic that goes into the treatment plant is retained, but that means that the plastic is then, it travels with the sludge fraction, which is then disposed of in different manners. Some places the sludge is incinerated, then of course the problem is gone. In other places the the sludge is maybe applied to agricultural land, and then we might see an increase in plastics in these areas.
Yeah, you mentioned a little bit about incineration. For plastics in general, not just microplastics, what would be beneficial or detrimental about incinerating plastic as a method to get rid of it?
Tricky question.
Yeah, I mean, I think it maybe also depends how you incinerate, how maybe how modern and how state of the art are this facility where this process are conducted. Because I mean, if there are effective also filtering system, then I mean what is emitted maybe might be not that like dangerous, but it really depends also where these things are done. Okay, also what Esbjørn previously mentioned about the treatment in wastewater treatment plants, this like 99% removal, it's maybe can be applied to modern facilities such as the one we have in Denmark, but of course not all the wastewater treatment plants are like the one in Denmark. So in other countries this removal percentage could be much lower, and even the incineration could be much less effective if the facilities is not a state-of-the-art one.
And at the end, we are living in a world that is changing. So maybe we can think about incineration for a way to reduce plastic pollution, but then we will be aggravating climate change.
Exactly.
So we have to consider that the different environmental problems are somehow connected, and trying to solve one, we can impact in other, increasing another environmental problem.
So it's very tricky actually to remediate.
And also the direct incineration in open space of plastic is totally not good for the health.
Of course.
So one thing is in a proper plant versus what is seen all over the world where they are directly incinerating plastics on open air.
Yeah.
I think, circling back just a little bit to your analyses, how long would it take to analyze in your lab everything that you've collected this week?
Good question.
I will reply on the easier way. We will say that for every 6 samples, we also run hour blanks. So we process the sample like in batches. So we will have 8 samples, and approximately from starting the process in the lab until we get our results, it can be between 4 to 5 weeks. So it's going to be a pretty demanding year for analyzing all these samples.
Yeah, also because
especially for the 1 micron samples, we don't have the method actually. So there we are trying to develop a method so that we can go down to this size fraction.
Yeah.
That's really interesting. Could you tell me more about how you're thinking about developing this method to analyze the super small particles?
So.
Okay, I mean, first of all, we have the instruments to do that. We know that they work. They can even analyze smaller particles than 1 micron, even go down to the nano plastic universe, let's say. But what we have to do is to develop a protocol to extract this plastic from the filters we are collecting now. And what we will do, we will use some model microplastics, and basically we will create a sort of fake sample by putting the microplastic into a volume of water, for example. Maybe we could even use some real seawater where we actually add some plastics, and then we will try to do apply certain steps where we try to reduce all the rest of the materials that we don't want in our sample, because they could interfere with our analysis. What we will do is basically to maybe add a certain known amount of plastic in the sample, and then we will try to see if at the end of our analysis we find the same amount, or if we find less, how much less we find. So this is so-called a recovery study. You put 50 particles, and then you see how many particles you get at the end. If you get close to 50, you are doing great. If you get only 2, maybe you need to start over and try another method to analyze. But basically, it's going to be a bit of a trial error, but that's how you improve your method. That's how you push science forward. You need to try, you need to be bold, you need to be, you need to try new things, and that's how things are done most of the cases, I would say.
We have just a couple more questions about your lab analyses. So, in your research so far, have you found a depth where you find a significant increase in the amount or size of the particles?
Deployed is the salinity and the temperature, and that largely determines the density of the water. And as previously mentioned, many plastic types, they have a density which is very close to that of water. So what we are doing in this cruise is that we are trying to target some of the depths where the density changes a lot, because the density of the seawater is not constant. So typically we will have lower salinity and higher temperature at the top, and then the bottom waters will be cooler and have a higher salinity, and that will result in a higher density. So as we go down through the water column, our hypothesis is that there will be some layers where the microplastics will be trapped depending on their density. And this we have been trying to target. So every station we have been at, we have done this profile, and then we have selected the depths of interest.
Very cool. I guess more on this, is there, not to like spoil your publication or anything, but are there any sort of results that maybe you're expecting from this week, or anything that you hypothesize specifically?
I will say, because one of the main motivation to do this study is that we know a lot what is on the surface of the ocean. We know there are higher concentration of plastic, that they are closer to the coast. Maybe in some open areas of the ocean they converge and accumulate in higher rates, but there is a higher part of the ocean that we don't know really their concentration. And what we also know is that there is a lot in the seafloor. So the main objective is to try to understand this vertical distribution along the water column, and the results, it's difficult to estimate because we are looking for this part in the water column where they might be accumulating. But one hypothesis is that once microplastics get degraded in the environment and they get smaller and smaller, are easier to sink along the water column, because their density is not the driving parameter governing how they are moving along the water column, I would say.
Plus, when they get degraded or degraded, they might change their density. So if you have a polymer or a specific plastic, like for example polyethylene, which is the most produced and used plastic in the world, that it normally should float on the surface because it has a density that is lower than the one of the seawater. When it gets old or when it gets exposed to the environment, its chemical structure changes and the density can increase, so it might also sink. Plus, there are a lot of microorganisms that will be attaching to the plastic, also dragging the plastic, from the surface to the bottom. And also plastic can be trapped in some sort of snowflakes that are called marine snow, which also favor the sinking of plastic. So there are a lot of parameters and variables to consider. That's why it's not an easy task, and that's why we put the best on the topic, But yes, we might expect some variation along the water column, but we don't want to spoil it too much, because we don't know, and some other colleagues found different results. So before saying anything, I think we should really do some hard work in the lab, and then we can maybe come back and tell you a bit more after we spend some months, trying to figure it out.
Very cool. Thank you so much for all of your explanations. I think I will wrap up by saying, or asking you rather, what your biggest takeaway from this week. Give the audience, maybe you all can go in order, what's it like for you to be out at sea? Because most of our viewers are watching at home. So could you give us a little bit of a glimpse of what that's like?
Well, for me, this is my first expedition, so for me, I think it's the whole experience in itself, like doing this continuous sampling 24 hours and yeah, see how it works on a ship. So for me, it's maybe not so much the microplastic right now, which will be at home, but the whole experience about being out and taking the samples for me is my precious takeaway here. Yeah.
Yeah, I think be on board is like kind of winning the lottery, let's say, and just all the Schmidt Ocean Institute team that has been helping us to make it possible and get all the precious samples that we are bringing back home. It's really amazing.
Well, I mean, I think you already covered most of the things that I could
And also,
say.
we escaped to be in the office. To be at sea is the best thing that we can do.
Yeah, it's true. I mean, I don't have much to add to what Janete and Laura already said. I mean, for me, this is not the first expedition. I consider myself very lucky. I've been at sea quite some times now. I've been sailing to the Arctic. I've been sailing in other type of waters, but I never been sailing on a ship this big, this new, this fancy, and also with a crew that is so helpful, so enthusiastic, and also so professional and passionate. Because you have to remember that scientists, they can be a bit annoying. They want to get the best out of the expedition, and sometimes they are asking more and more and more. So I would say that the Falkor 2 crew has been really good with us, and it helped us to get the best out of this expedition. What I bring back home as a take home is like another great experience at sea. I love field work, and I think to really understand the environment, the best way is to be out there. And moreover, I mean, yeah, you skip to be in the lab, which is also very cool.
Yeah, for me it has been really a great experience. I think you have put many words on it. I fully agree. I think one thing for me that was really exciting was the opportunity to take samples at 3 kilometers of depth. Because so far I've only been sampling in the waters around Denmark, where we are restricted to maybe 60 meters of depth. So this is a completely other world.
Yeah.
Very cool. Well, thank you all so much for joining me today. I'd also like to thank the audience for joining us today. Thank you all so much for your questions and for your amazing science and your wonderful explanations. It's been such a pleasure. It's been such a pleasure to have you on board. And I guess I will sign off on the stream now. I just wanted to remind the audience that we will be continuing with our dive streams the next expedition. So keep your eyes and ears peeled for that. And yeah, I'd like to wish everyone a good morning, good afternoon, good evening, wherever they are. And yeah, stay tuned. Yeah, thank you all so much.
Thank you.